All right, apologies for the late start. My computer is very slow. And I'll post the live link in a second once I get a chance to do it. All right, let's just dive into the chapter, and then we'll go over some maybe homework questions from last week. And just on another note, make sure that your grades are up to date and everything. So I think I should have caught up on grading, I believe. And so I'll hand back some papers, but make sure everything is correct and I'm not missing a mini stack somewhere. Should be reaching the end. I do have somebody's nameless chapter 5 homework. I'm not sure who this is. So if you're missing a grade and you turned it in, check if that's yours. All right, let's just dive into our acids and bases. So kind of our last chapter. And so we'll start off with our general properties of acids. And so you may know this from, tasting some acids. You can think back to things that you've had that are acidic, right? Lemons or other citrus fruits. And so they have that sour taste, of course, that's very distinct, or like those Zotz candies. If you haven't had them, I could grab some. Those are fun. And so these acids, we've seen this in lab, but we've seen how they can dissolve metals, the acids, so like hydrochloric acid and magnesium. And then, of course, they can also neutralize bases. You did a little bit of that in lab, or you will do it on Wednesday with the acetic acid and sodium hydroxide. And then if you have an acid, you can test it with blue litmus paper, and it goes from blue to red. Of course, we kind of tend to prefer the universal paper anyways. And you'll play with the universal pH paper in lab, and of course you see that gives you a wider color range. And so these are just some common acids. And some things to note: hydrochloric acid, that's a component of your stomach acid. That's kind of interesting, right? So your stomach produces acid to help break down your food. Then sulfuric acid, that can be used in like fertilizers or explosives, also batteries. Nitric acid, again, more fertilizers, explosives. Acetic acid is, of course, vinegar, so used in food preservation. Y'all are probably familiar with that. Citric acid, so this is right what we have in lab, that little powder, but it can also be used to make like candy or in other foods. They also use other like fruit sugars, maltose or malic acid. Carbonic acid, so this is going to be in your beverages or like your sparkling water. So, I have my sparkling water here, and of course this is actually going to be a little bit of acidic because of the carbonic acid that's formed with the CO2. And so, right, that could get into other arguments for nitro versus CO2 canning, but we won't go there. And then hydrofluoric acid, so this is pretty nasty, hydrofluoric acid, but it's essential for like glass frosting, or they usually clean the metal surfaces for like making chips, so like your silicon chips. And then phosphoric acid is also used in fertilizer manufacturing or as a biological buffer, so you see a lot of phosphoric acid-based biological buffers. And then usually there's a little bit of phosphoric acid as well in like your soda, like a Coke or Pepsi. Those have a little bit of phosphoric acid. And then as an introduction to kind of your organics, so organic acids all have this carboxylic acid group. And so this is that COOH thing, but we'll draw it out. So this is a carboxylic acid group. So a carbon with a double bond oxygen and then an OH. And then this is what's called the acidic proton, aka the one that leaves and gets deprotonated. And then the citric acid, malic acid, they again have similar structures, so you can kind of see that carbon on the end that's double bonded to the oxygen, and then the OH group there. And then this is just 4 carbons, this is 6 carbons, so just different carbon lengths. And so now we've switched to bases. And so bases, I don't know if anybody has ever gotten their mouth washed out with soap, but if you have, you know why, because it tastes kind of bitter, or if you just get soap in your mouth accidentally. And so often, these bases are poisonous, so obviously that's why you wouldn't drink your Drano or anything, or ammonia. Those are all pretty nasty. Milk of magnesia, though, so that would be a basic thing that you could eat. So add to that milk of magnesia. So sometimes people take that, right, if you have an upset stomach. And then, again, a lot of these bases feel slippery. So you notice that with soap. You probably don't want to be touching bleach, but, if you do kind of touch some bleach, you notice it has that slippery feel. And of course, right, bases will neutralize our acids. And then we have to use the red litmus paper, and it goes from red to blue. And so here are our common bases. So we have sodium hydroxide, potassium hydroxide, and these are used pretty interchangeably. So a lot of them are in like soap production. And then we also have so sodium bicarbonate. So this could be used. So this is baking soda. And they often use any one of these. So sometimes, I think they actually just did it to our Medford water. I think they actually picked sodium hydroxide to add to make it just a little bit more alkaline. So they're trying to adjust the pH a little. But you can use other things like sodium bicarbonate to kind of add to the water. So it kind of depends. We won't get into water chemistry, but they're just trying to minimize kind of ions in solution, kind of keep it at the right pH. And the thought is, if you keep it a little more alkaline, then it won't be leaching like metals from the inside of your pipes. I'll just do water pH adjustment. And I'm not quite sure why they picked sodium hydroxide over other bases. Again, it probably depends on like the other counter ions in the water, or maybe they don't want carbonates to make insoluble products, so those are all things you have to think about. And then sodium carbonate can also be used in soap manufacturing, or again, water softener. And then ammonia is pretty important just because it's a fertilizer, and of course it can also be in explosives, but mainly fertilizer is its big relevant use. All right, so now let's look at this hydronium ion. And so all we're saying is that when we have an acidic solution, we don't really have H+ ions. And so what we mean by that, and we can look at 2 different scenarios. So we can have what's called this water autoionization. And so that's where water can basically protonate or deprotonate itself. And so what does this mean? Well, we have 2 water molecules that are staring at each other. And then a small percentage of them can become ionized. And we'll just have, so this oxygen is going to attack our other water, deprotonating it. And so this forms our hydronium ion, which is our H3O plus, but we're going to learn that basically we still just abbreviate it as H plus. So hydronium, and then we also have, of course, hydroxide if we've made hydronium. So it looks like that. Or let's see how else this could play out in solution. And so now let's take vinegar. So this is vinegar. I drew it pretty short-handed. So this is, right, my CH3 down here. And so vinegar, again, same thing. It's called acidic in solution since it makes our H plus ions. But again, we're not really making H plus. We're really making hydronium. And then we would have our acetate. So now this is acetate, like in our sodium acetate. All right, so just recap what we're saying. So all we're saying is that we can't really just have, naked H plus floating around in solution. It's just not going to exist because it's going to be so reactive that really what happens is that it gets picked up by our water species. And so that's where the hydronium comes into play. But now we're saying, okay, even though we know this exists, chemists still just use H plus. And so these two terms are used interchangeably. So if you see hydronium or H plus, it's referring to the same thing. So that's all that is saying. And, oftentimes we use just the abbreviation, right? So I'm showing how our strong acid disassociates, but again, I'm just being kind of short-handed with it and showing it as H plus. And we can write in parentheses, oh, okay, well, we know that's really hydronium. All right, let's go through our definitions. And so this is just kind of the quick summary, and then we'll kind of go back to this summary. And so for our purposes, we'll start with the Arrhenius theory. And this is just our basic, easiest definition of what is an acid, what is a base. And so now we say, well, acids are anything that produce H plus ions in solution. Again, right, we know they're not really H plus, but that they're hydronium. And so we can have our HCl disassociating. We can see how our other acids fall into that, right? Nitric acid, hydroiodic, hydrobromic, all those disassociate, right, and clearly make H plus ions in solution. And so same thing with our base definition. Again, it's our simplest, and we're saying bases produce hydroxide ions in solution. So we can think about mainly our group 1 and 2 bases disassociating. So I'll just put group 1 and 2, especially, magnesium hydroxide, potassium hydroxide, etc., etc. We could go on. And so write those clearly disassociate into our cation and anion. And if we have a base, right, our hydroxide anion. And then, of course, in our simplest acid-base reactions, so just thinking more specifically, HCl plus sodium hydroxide, and then we do our double displacement to, of course, form our salt plus water. And it's kind of trying to help you and kind of remind you, right, oh, H2O is HOH as well. So you can see those two components, right, your H plus part and your hydroxide. And so, again, neutralization reaction, forming salt and water. And so the problem with this is that it's too narrow of a definition. And so, right, it doesn't explain why ammonia is basic, even though there's no OH ions. It also doesn't explain how sodium carbonate or sodium oxide also form basic solutions. And it doesn't explain why CO2 can form acidic solutions. All right, so now we go to our next definition of acids and bases. And so now we go to our Bronsted-Lowry acid-base theory. And so this was just based upon the need to refine, right, our Arrhenius definition. So, okay, we see its shortcomings. And so now we have our new definition. And so for Bronsted-Lowry, any reaction that transfers a proton from one molecule to the other is an acid or base. So irregardless of whether it occurs in an aqueous solution or if there's OH ions. Oh. So then kind of the key, and we'll zoom out because this is our key here for acid base. And so our acid is defined as our H+ ion donor. And so that must mean that our base is our acceptor. And so we'll see how that works. And then we usually try to identify our acid-base species. And so previously, our initial acid species, kind of HA, is shown here. Then we react it with our base, and then we form now our deprotonated conjugate base. So formerly the acid loses a proton, becomes our base, and then we make our new conjugate acid. And so then we can see how our Arrhenius definition still fits in. So we have acid dissolving in water, and water here is acting as our base. And then our base, right, it has our 2 electrons that can pluck off our hydrogen and make our new now conjugate acids, now our new protonated species. And so just compare, right, our base gained a proton to go from base to conjugate acid, so plus a proton. And then our conjugate base, right, started as an acid and then just lost a hydrogen there. And so let's see this for something that's not as simple as HCl. And so let's kind of go through it for ammonia in more detail. And so now this is showing why ammonia is a base. And let's draw it out. So if we draw our Lewis dot structure, right, there's our ammonia. It has 2 electrons there. So that's how it can act as a base. And then we have water. And so water can be an acid or a base depending on the scenario. And so now in this case, ammonia is going to pluck off one of these hydrogens. And now we make ammonium. And then also still have our hydroxide. And so now this tells you why in lab today you just have ammonium hydroxide as ammonia. So this just goes back and forth in equilibrium, and right, so you can reform your ammonia from your hydroxide, deprotoning off your ammonium here. So notice, right, I'm using those half equilibrium arrows to kind of show that this can go back and forth as well. And then we have our species labeled, right? So this was our base. Water is acting as our acid since it got deprotonated, right? So it's our H plus donor. Then this became our new conjugate acid species as it gained a proton, and then leaving us with our base.
What does that mean, conjugate?
So conjugate just means you have these conjugate acid-base pairs, and so they're just different by a proton. So notice, right, your base ammonia gained a proton to become ammonium, making it the conjugate acid. So the conjugate acid of your base just has, again, an extra proton. So same thing, right, with your water hydroxide. So now hydroxide lost a proton, so this would be your acid-base pair. And so that's what's kind of nice, is being able to show the acid, the base, right, the conjugate base, and kind of conjugate acid as well. And so we can also think about this in context of our lab. So we have, right, our acetic acid. And actually, let's show it with water, because again, we want to show its equilibrium. And so this is our acid. Water is acting as our base. Then, right, acetic acid can get deprotonated to make acetate, right? Or this could be sodium acetate. We didn't put a counter ion to it, but just kind of thinking back, right, to the chemicals you were given. Oh, sodium acetate. So now this is our conjugate base. And then, of course, we make hydronium. And so it's just good to be able to recognize, too, these acid-base pairs so you would know how to make a buffer, right? So that's how you know to make an acetic acid buffer that we need sodium acetate, right, or whatever appropriate acetate salt. And so that's what we've been seeing. So our conjugate acid-base pairs. And again, right, our original base becomes our conjugate acid, and then our acid is our conjugate base. And then it's just saying, right, that we can kind of do this reverse reaction. So just like we had our ammonia plus water gives us, right, ammonium and hydroxide. So now we can take that ammonium, re-react it with water, and then form our base plus hydronium in this case. So it kind of depends. So I went ahead and just took our conjugate acid and reacted it with a new base, but you could also just flip it, right, and react our ammonium plus hydroxide give us back to ammonia. And again, they are just different by a hydrogen. So there we have our conjugate pairs. So our base and our acid, acid and base. So we'll do this, and then before we look at this, what's the problem with this? Is this an appropriate acid-base pair or not? What do you mean by balanced?
Oh, I guess what do you mean by pair?
So is it an acid-base pair, like this sort of?
Right, so there's two hydrogen in for the H3O is not a base.
Well, H3O would be an acid
Yeah,
species. But I think you kind of said it. What's the problem, though?
There's
Yep, so the difference is too large, right? So 2 proton difference. So that means it's not difference. So not acid-base pair. So that's good. So this is one way you could get tricked on an exam or something, is it says, you know, pick the appropriate acid-base pair, but then this one, oh, that's too big of a difference, so that's not an acid-base pair. But then hydronium and water, right, that would be appropriate. They're one different. And then water and, bless you, hydroxide, right, that's appropriate. They're only one hydrogen difference. All right, so try this problem down here. So identify who's acting as the acid, who's acting as a base, and then of course, then the corresponding conjugate acid and conjugate base species. All right, what did we get for A? So what did we think the sulfuric acid was acting as?
Bond
So our acid, so then if this is our acid, what does that make? Water. So our base, excellent. And so then what's our HSO4 species? So conjugate base, excellent. And then this, conjugate acid. Questions on this first one here? So let's try the next one. So then we have this HCO3 negative species plus water gives us carbonic acid. So then what's our HCO3 species? Acid, base. So our base, excellent, and right, you're just kind of comparing what happens to it, right? So it picks up a proton, so it's our proton acceptor, so that has to be a base. And so if this is a base, what's water then? Acid, I think I heard some acid whispers. And then that leaves H2CO3 as what then? So our conjugate acid and then our hydroxide. So conjugate base. Any questions about those? All right, so let's keep looking. And so I didn't bring the demo, so we'll save the demo for Wednesday, looking at kind of the strong versus weak. And so again, I feel like we've been saying this a lot, but we'll say it again. So our strong acid is a strong electrolyte. And so it has nothing to do with how dangerous it is or anything. It's just how much does it disassociate. And so I'll bring up our HCl again. Right, so fully disassociates, or nitric, right, both of those are great examples. And then for those, I usually use our single-headed arrow to show, yes, complete disassociation, so it's not going to reform our nitric acid in solution. And then our weak acid, so it's a weak electrolyte, again, has nothing to do with its strength. Right, so I'll bring up HF. So HF is pretty nasty, right? You don't want to get it on you. And so the problem with HF is that it doesn't really burn. At least I've never made contact with it. That's just what I've been told. But the problem is HF then will absorb into your skin and then dissolve the calcium in your bones. And then that calcium could potentially, right, re-solidify then somewhere in your arteries. And of course, the only question is where. And that's not fun, right? So it could be in your brain, and then that could be bad, or in your heart, that would also be bad. So that's why I kind of stick away from HF. That's under my list of things I don't want to. Well, I'm not sure how often that happens. So you have this little like calcium antidote thing. So if you're working with HF, you would have that. So if you suspected you got some, you would put that calcium product on you, so it binds to that calcium as opposed to anything else. Yeah, but that being said, I don't actually know what the incidence of getting like any HF on you is, because people are pretty, yeah, and sometimes with these, so I mentioned, right, they're used for like silicon chips. So then you have to go into like this clean room thing anyways, and you're wearing the bunny suit and all that stuff and working with HF, so that probably helps, yeah, keep people kind of in the safety mentality. But that being said, so HF is still considered a weak acid simply because of the equilibrium. And so that being said, and this will kind of come up later as we continue talking about this chapter, but then there is a danger in like sodium fluoride salts or you know, if you're potentially making fluoride as a byproduct, because now what can happen is then fluoride will react with our water here. And then, so it's going to pluck off a hydrogen and then make a little residual rate HF back in solution. So just something to keep in mind, you know, if you're doing chemistry, you're doing some sort of reaction, you're making sodium fluoride, then you have to make sure you neutralize your waste so you don't have HF running around. And so again, same thing, strong base means it completely disassociates. And then our weak base, well, we'll just give it away. They tend to be amine base. So of course, right, we have ammonia as the one that we know, we see, we work with, but I'll bring up this bad boy. So this is methylamine. Anybody familiar with methylamine? You guys watch Breaking Bad? No? You guys gotta watch Breaking Bad? No? You've watched it? Yeah, so do you remember methylamine? Yeah, so methylamine, there's this big scene where they like hijack methylamine. Anyways, methylamine is a super highly regulated substance thanks to Breaking Bad because you can make meth with it. One of the many ways to make meth, though, let's be real. But my whole point was that anything that's sort of this amine thing can be a base as well, is a weak base. So just like ammonia reacts, right, the methylamine can do the same sort of thing and take a hydrogen, and then this makes methylammonium. So methylammonium. And we won't go into all the variations of this that you can have, but basically your amines tend to be your weak bases, so can't really think of anything else that we would see. And then this is just kind of general trends to help you. And so other things to note, so this kind of goes along with it. So if it's positive, here's what I'm looking for. So a cation is a stronger acid than a neutral molecule. And so all that's saying, if it's positively charged, right, then that tends to be an acid. So you can think of, well, it has here, right, ammonium. So this is an acid, and then this is a base, right, and then this would be even more of a base, is what it's saying. So same thing, right, with our cation. So this is a stronger acid than the neutral water, and then of course, right, this is a base. So kind of that trend. But also with that, right, is, I want to say, so cations are usually acidic. So that's basically what we're saying here. And then other kind of general trends is the more oxygens, the stronger the acid. And so just comparing nitric acid versus nitrous.
Are there any common cations that aren't acidic that we need to know about?
No, I really can't think of any. Yeah, because you could get into that, like aluminum is amphoteric, but aluminum does like weird things. And mainly we just treat it like an acidic metal anyways. So. And then this is useful if people want this printed. I could go print out some copies. But let's kind of take a tour of this. And so up at the top, so we have 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4. I think we're missing. I'm trying to think of which acid we're missing. But these are your main strong acids here. I think you're missing one of the perchloric acids. But these are strong acids, and it's telling you this, right? So it's saying undergo complete acid ionization in water. So that's what that is saying. And then look at their corresponding conjugate bases. So this is also useful, but let's break down what it's saying. So it says, do not undergo base ionization in water. And so again, for comparison, we had said that fluoride, remember, it could react with water and reform HF, and of course make a base. But now we're saying because our equilibrium, right, lies all the way to the right, so just rewriting, let's do HCl again. So we're saying our equilibrium lies all the way to the right, and so our chloride cannot do the same thing. So, right, if you dissolve, you know, sodium chloride in water, it's not going to make HCl, so it's going to be neutral, and so I'm going to put, right, this does not happen. So we're not going to reform HCl. So that's what this is saying. So that's useful. And then now below it, so hydronium and water, right? So those would have equilibrium back and forth. And then now these are just our conjugate base pairs. So their difference is by hydrogen, phosphoric acid, right? Dihydrogen phosphate, HF, fluoride. And then we get into the nitrous and nitrate. There's acetate and acetic acid. And then now we get down to here. And so this is saying, right, that like our ethanol isn't going to deprotonate. And then sulfides. So this would kind of add. But this is kind of your most useful section to determine your acid-base pairs, and then again determining who does not reform. And then so blah, 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 this goes back to our equilibrium constant. So do you at least kind of vaguely remember K? Remember we had said it was roughly products over reactants. We could go back, if I can even find it. Which chapter was it? I want to say it was 7. I could be wrong. Might have been further back. Of course, now I'm trying to find this. Oh, here we go. So remember these equilibrium expressions, and right, it mattered their coefficients. We raised them to the power of their coefficients. So do we remember this? Yes, vaguely? All right, so at least, oh, bless you. So I just wanted us to kind of orient ourselves because it's the same K. And again, right, we can just look at the simplified approach, products over reactants. You can also kind of think about writing the expression in terms of HA, but right, HA gives you H plus and A minus, right? So our acid, and conjugate base species over, so K would be H plus over conjugate base over how much is still together, basically. So disassociated over associated. And so now all we're saying, okay, well, if we have a strong acid, right, our Ka is going to be greater than 1, since we said, well, it's almost 100% ionization. So these will be dominating the concentration. We should have almost negligible HA. And then again, there are 6 strong acids. So if you want to highlight that or refer back to your other sheet. And then weak acids, the important thing to note is their Ka is less than 1. So again, only a small fraction is ionized. And so this is a good pictorial representation. So just showing you, right, many of the HFs are still coupled together, and then a few of them have disassociated. And so again, right, it lists just more common acids, but this is certainly not a complete list. And let's see, so other things we want to say is at least we want to appreciate who's stronger. And so we have our acid dissociation constant. And so this is larger, our acid dissociation constant, than our hydrocyanic acid. So we're comparing for our chlorous acid, 1.1 times 10 to the negative 2 versus 4.9 times 10 to the negative 10. And again, you're just thinking about what the K means, if that helps. And so if we have, right, a greater number, more is disassociated. And so now we're saying our chlorous acid is stronger. So just based off the power. And so blah, 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 we had already derived this of what our Ka expression was, again, based of products over reactants. Water is not included in the equilibrium expression since it's run in water, so concentration doesn't matter for water. And then this is just another table of our acid dissociation constants. And so we should at least point out the relationship between pKa and Ka. And so pKa is just equal to the negative log of Ka. And so chemists tend to like pKa just because it's an easier number to work with. And so the smaller the pKa, the stronger the acid. And let's just pull up a calculator. So again, make sure your calculator that you want to use on your exam works correctly, is in the correct base 10. And so we can practice. So we want to get our pKa. I'll just get my negative log of 1.1 times 10 to the negative 2. And then I forget the exact mathematical rule of y, or the derivation as to y, but you add a sig fig. So your log, right, you have 2 sig figs in for your log value, but doing the log means you get an extra sig fig out. So then you put in 2, but report out 3 for the log. So then you get the pKa of 1.96, which matches what the table has. And then, of course, you can also do 10 to the power of your negative pKa to go back to your Ka. And so that's our Ka again. So just our log math. And now we can just appreciate the chart. And so notice, right, increasing pKa value just means lower acid strength. And again, pKa would be more relevant if you went on to CHEM, and then chemists love to talk about pKa's and who's more acidic and not. And again, just appreciate the Ka. This could be useful if you need help with your equations. You got this disassociation shown here. And again, just representative acids. So you might see HF. Here's formic acid. Benzoic acid, acetic acid again, right, good old vinegar. And then phenol, so this is a pretty weak organic acid. All right, let's take a little break there, and then we'll continue on with pHs. So we'll take our 10-minute break. Then I have homework printed out if you didn't get that. I'll try to hand back some papers. Oh, that's the wrong E.
Oh, is it?
Yeah,
Sorry.
so that's the other
Well, that's why
E.
I'm having issues then.
Yeah, so then the times 10 is this E.
Oh,
And
okay.
then -2.
I'm sorry, I must be confusing it with my algebra class.
Yeah,
So
because
do
E,
negatives log, like you just put a negative in front
Yeah.
of the log, okay.
That's it. It's
And then
it
it's
is-
just log 10.
Okay.
yeah, E is if you're using, what's E, like 2.3?
Yeah,
or something?
2.71.
Yeah, because this is the one Professor Otto told us.
Mhm.
So,
Yeah, but not
Yeah,
for.
not for this one.
Yeah,
Scientific
not,
notation.
not for the times.
okay,
Yeah.
sorry, thank you.
No,
I
no
was
worries,
very
that's-
confused.
That's why I always
So
say
what E's
practice,
on
practice.
There's
So we're on the right E's.
2, 3, 4.
Yeah, I was gonna also ask how to do the E part online.
Yeah, so then it's the second E, so that E, second E.
Okay.
Yeah, and then you just do -2. So the PE means times 10 to the whatever. Oh, here's my paper. Oh, Taylor just left. A fat sack of stuff. Yeah, we'll leave the paper to Taylor. Oh, yeah, do you still have the candles in lab?
Yeah, I do. I need to go pick those up. I'm sorry. I can take them home today.
I just assume you want your candle stuff back.
I just keep forgetting them. I'm like, oh wait. It's all in lab. Well, yes, last lab, yeah.
Yeah, I just saw it there today. I guess we'll continue. All right, so back to acid-base chemistry. And so this is just going over the autoionization of water again, but then this is kind of cool because we're kind of getting at, well, why is our pH scale how it is? And so, right, it mentions about 2 of every 1 billion water molecules form ions through this autoionization process. And so again, depending how you want to think about it, it could either be as simple as water disassociating, as shown here, or of course, right, just remembering that this doesn't actually exist. And so really, right, it's hydronium. So that's where the 2 water molecules are shown, and you can think about them, again, reacting like we saw earlier. So lone pair, right, taking off the hydrogen of another one. And so now this is kind of where our pH scale comes into play. And so at some point they determined this. And so they determined at a neutral pH that hydronium and hydroxide are equal. And so we get this relationship. And so now, again, we're kind of getting at, well, why our pH scale is 0 to 14. And we have, okay, well, at a neutral pH, at a pH of 7, the hydronium and hydroxide concentrations are the same, and they're both, again, 1 times 10 to the negative 7 molarity. And this is at 25 degrees Celsius. And then, so the other important relationship, and now this is kind of telling us why it goes to 14, is that our product is always the same. So meaning our concentration of hydronium times hydroxide always has to equal 1 times 10 to the negative 14. And so this is also called Kw, and at different temperatures you would have slightly different Kw constants, but for our purposes we're only going to focus on 25 degrees Celsius, so you don't have to worry about that. And so that means, right, if we measure one of the concentrations, we can solve the other. And so then this leads to this relationship that our hydronium and hydroxide concentrations are inversely proportional. So if one increases, right, the other has to decrease. And so, of course, all aqueous solutions contain some amount of hydronium and hydroxide ions. If they are neutral, again, you would have equal amounts. And then acidic solutions have larger hydronium concentrations than hydroxide. And so, right, your hydronium would be greater than 10 to the negative 7, and then basic solutions have a larger hydroxide than hydronium concentration. So see if you can look at this and determine if it's acidic, basic, or neutral. And then we'll reveal more tricks. So what do we think about A? Acidic, basic, neutral? Any thoughts? So how much is the hydronium concentration when it's neutral? What? Yeah, so right, let's keep that in mind. Okay, so we have hydronium, right, at pH 7 or neutral. You said it was 1 times 10 to the negative 7. So then we just have to ask ourselves, so then is 7.5 times 10 to the negative 5th, is that greater or smaller than our 1 times 10 to the negative 7? So then which is it? More, less? More, right? So now it's more acidic, so more than our neutral, so then that means it's acidic. And then what about for B then? So 1.5 times 10 to the negative 9. So right, compare that to your neutral. So is it more, is it less? So less, I hear whisper over there, so if it's less, right, then it has to be basic, since again we're looking at the hydronium. And then what about this last one? What do you recognize? What number does it match with? So 7 or neutral, exactly. And so this was a good exercise in practicing our powers, but you may know this formula, and this is probably more helpful just for our brains. And so our pH is just expressed then as the negative log of our hydronium concentration. So if we go back to our problem here, now it makes it a little more obvious. So if we take our negative log, let's just do our first one. So negative log of 7.5 times 10 to the negative 5th. And so now we get 4.15 as our pH, and so we can clearly see that that's acidic now. So 4.15. And so same thing, let's plug in B now just for fun. So negative log of 1.5 times 10 to the negative 9th. And so we get 8.82. So now we can tell, at least really tell, that it's basic. And so this is just kind of giving us a range and some context. So like we said, our stomach acid is pretty acidic, so 1 to 3. So of course that's why they always say, right, you know, wash your mouth if you throw up, and you know, symptoms of bulimia are going to be damage to the teeth. And then limes and lemons. So I always, you know, suggest don't, you know, soak your teeth in limes and lemons either, or don't, you know, have a bunch of orange juice and then brush your teeth, because that could also wear away at your enamel. So pretty low pH. So soft drinks as well are also acidic. So of course, same thing, right? All that can wear on your tooth enamel. And then now we get into your fruits. So still fairly acidic, but kind of going up now. Wine, you know, acidic as well. So again, same thing. You can think about your teeth. And then beer starts to get kind of closer to neutral, to 4 to 5. Rainwater, this could be like kind of acid rain, is about 5.6, or could be lower if it's acidic or more polluted. And then human blood, notice it has a really tight range, so your blood is a buffer solution. Egg whites are also pretty tight range. And then there's milk of magnesia, like we mentioned. If your stomach's upset, you might take that. And then household ammonia, so that's 10 to 11. And then, of course, our sodium hydroxide is going to be 14. And then if we want to go the other way, so let's say we want to find our hydronium concentration from our pH, we can just do the opposite. So now hydronium is equal to 10 to the power of our pH. So if we did, I'll just do our 4.15 again so we can go back and forth. And, oops, sorry, negative. Let me try that one more time. 10 to the power of negative 4.15. And now we get back out our hydronium concentration. So 7.1 times 10 to the negative fifth. Little rounding error discrepancy. And so, like we've seen, this explains why our pH scale goes from 0 to 14. We had our Kw constant. And again, right, our relationship. 7, of course, was neutral. It's in the middle of that. And then our hydronium concentration is just roughly shown there. And so now see if you can calculate the pH. Although that being said, I kind of spoiled the next section, so if you need to use this, you can. So we can see very similarly, we have our pOH relationship that just gives us our concentration of hydroxide. But see if you can try this first, and then we'll jump into the pOH. Some people might find it useful. All right, how did A turn out? Did we get a pH for this one? What did you get? So 3.7, do you have another digit?
Oh, yeah, 4.
So 3.74, so that looks good. I'll plug it in, but just kind of a quick hint. So look that what your power is, so it's 10 to the negative 4. So your pH should be roughly that. So the 3.74 already sounds great. And let's just all plug it in so we're all on the same page. All right, so that looks good. But then what did y'all do for this next one? What are some thoughts? There's a couple of different ways we could get our pH for this. So what could we have done? for our relationships from earlier. Did we try anything? Did we get an answer? Brooke, any thoughts?
Well, so isn't OH supposed to or OH plus H3O or something equal something with 14?
Yeah, so let's go with that. So right, remember what it was. So it's hydronium times our hydroxide concentration, so they're multiplied, right, equals that 1 times 10 to the negative 14. So this was kind of the key thing that we needed, or at least one of the things, given the information that we have so far. So once we get to this POH one, we're going to kind of re-go over all the formulas. But yes, based on what we have, okay, let's start with this. And so now let's solve. And I'll do the algebra. So now we're saying, well, 1.3 times 10 to the negative 2 times, so we want to solve for hydronium is equal 1 times 10 to the negative 14. So that's just right, the KW by definition. And again, this is why you can add them, the POHs. Well, we'll get there. So 1 times 10 to the negative 14 divided by our hydroxide concentration. And so now this is our hydronium concentration. So let's write that down. So now this is 7.69 times 10 to the negative 13. And so now let's get the pH of that. So negative log of our hydronium. And so we get 12.11. So yes, this would be basic. But let's continue on with this kind of thought, right? So this is one method. And so I kind of gave a little hint, and it says, well, what is POH, right? So we can just express our POH. So instead of, right, expressing it as hydronium, we can express it in terms of hydroxide. And so we have the POH concentration, right? We can get our, if we have our hydroxide concentration, we can get our POH, or vice versa, right? We can go from POH back to hydroxide. And so let's plug this in, right? So let's say we wanted to do the other method. So now let's get our POH instead. So it's equal to our negative log of the 1.3. So let's see what that gives us. So negative log of 1.3 times 10 to the negative 2. And so that gives us a POH then of 1.89. So POH. And so we're kind of missing the last little step, but I think we're almost there. And so now this is our key next step here. And so we have that our pH plus our POH is equal to 14. So this is useful. Or, right, it goes through our small derivation of that, or it reminds us, right, our KW product constant. So we said hydronium times hydroxide has to equal KW. And then they just did the derivation, right? So they took the negative log of everything. And so negative log of hydronium plus the negative log of hydroxide just equals to pH plus POH equals to 14. So then we can go back to this problem. Oh, okay, well my POH was 1.89. And then if we wanted pH, well now we can use our new relationship. So POH plus pH is equal to 14. So now pH is equal to 14 minus 1.89, which should give us 2.11 based off of my, or 12.11, and indeed, it does. So either way, right, you get the same answer there. Does that make sense? Feel good? And so I kind of like the acid-base chapter because of that, because it feels like you can check and double check your work in a circle. And so this is our graph, just kind of summarizing that. So just reminding us, so our pH scale goes from 0 to 14. And then we said pH plus POH has to equal 14, and we see that, right? So you add these two up, they equal to 14. They're both 7 at neutral. And then, of course, POH, though, goes from 14 to 0, where 0 is your most basic. So they're opposite. All right. And then, so our buffer solution, we won't go too much into depth, but our buffer solutions are just defined as solutions that resist a change in pH. And again, the key part is how do we make a buffer? So it needs a weak acid and its conjugate base. And a good example would be our vinegar or acetic acid. And then the conjugate base, right? So it makes acetate. So then the appropriate base would be sodium acetate. And then so same thing if we were looking at a weak base then and the conjugate acid. Well, I gave a hint. Most of our bases have to be ammonia base or amine. And then it's conjugate acid salt, so right, ammonium chloride or whatever would be good. So some sort of ammonium salt. So there's our acid-base pair, right? That's why it's good to recognize our acid-base pairs. And here is another example of a buffer system of our blood. So it has our carbonic acid and then our hydrogen carbonate ion. Again, just notice, right, the difference of the proton. So there's our acid-base system. And now it's just telling us, so we mix ideally equal amounts. That gives us a greater buffering capacity. And this is very wordy, but all it's saying is that, right, you have your component that reacts with your acid system. And so let's say, right, we have our, this is focusing on our acetic acid buffer system. And so, right, it's saying, and let's just emphasize that, right? So this is for our acetic acid acetate buffer. And so this is what it's talking about. And so now it's saying, right, you add some base and it's going to be neutralized by your acid. So in this case, right, our vinegar or acetic acid. And okay, and then notice, right, what it makes. So then it makes your conjugate base here, or A minus, just how we've seen it in its different forms. And then that's kind of why, right, it resists the change. So you make your conjugate base, and then of course, right, this can always go back and reform acetic acid in equilibrium. So then your pH should barely change, and I think you got good results in lab with this. And then so same thing, now we have acid, but now it's reacting, right, with A minus, aka our sodium acetate. And so now it's just our conjugate base part of our buffer system, so we could add acid, it reacts with our sodium acetate, and of course reforms HA here. So this is now just our original acid, and then of course our salt. And then obviously again equilibrium, right, Le Chatelier's principle can go back and forth as well if it needs to. And then for our purposes, if we're given kind of what's the pH of a buffer solution, then we can use Henderson-Hasselbalch. So pH of a buffer. And I'll just, a couple of other things to note. So I like the formula, So I like the formula in this form. So pH equals pKa plus the log of base over acid. And base, again, is A minus, acid is HA. But you might see a different form of this formula, and that's only because if they put acid over base. So I'll write it over here. So pH is equal to the pKa minus then the log of acid over base. So that's why you might see variations in that formula. I personally like this one just because I want to keep base over acid straight. But I was just trying to pull up your homework. Okay, what else do we need to look at? Oh, this is important. So now this is classifying salts as acidic, basic, or neutral. And so we should kind of run through this. Oops. And so let's kind of look through what it's saying. So the first one says if our salt cation is a counter ion of a strong base, okay, right, so that means where did our sodium come from? And you kind of just pair it to its most usual base, right? So sodium, it probably was paired with hydroxide. That fully disassociates, so sodium is neutral. And then it says the anion is the conjugate base of a strong acid. And so, right, our chlorine comes from HCl. And so neither one of these can reform. And so let's actually do our little analysis. So I like to go sodium chloride, and then we do sodium. It again came from sodium hydroxide. So that means our sodium is neutral. And again, this has to do with its disassociation, right? So sodium hydroxide completely disassociates, equilibrium lies all the way to the right, so it's not going to reform sodium hydroxide. So same thing with our chlorine, right? It came from HCl, strong acid, so equilibrium lies all the way to the right, so it's not going to remake our acid. So chloride is neutral. And then, so same thing, we can do our analysis for this one. So where does calcium come from? What base is it associated with? So don't overthink it. What is it? What's calcium paired with if it's a base? So what are bases normally paired with? What defines a base? So neutralizes the acid, but what group do we usually see in there? Like what makes a base? The presence of what ions? Yeah, hydroxide, right? So then calcium, so going through the analysis of calcium nitrate, so calcium comes from calcium hydroxide. So that's, right, it's the counter ion of a strong base. Fully disassociates though, so it's not going to reform. So calcium is neutral. So same thing, where does nitrate come from in terms of acids? So what's its acid pair with nitrate? So don't overthink it. So how do you make an acid out of nitrate? Yeah, so right, so then you have HNO3, so that's nitric acid. And then what do you remember about nitric acid? Was that a strong acid, weak acid? So if we forget, we can always go back to this chart down here. So this is why I like this chart, right? Because now it's reminding us, oh, nitric acid, complete acid ionization, right? And then it's reminding us, yeah, so it's a strong acid, and then the nitrate, so it's telling us, right, it's not going to reform. So that's what this means and how we can use that. So then, yes, right, equilibrium lies all the way to the right. Nitrate isn't going to reform nitric acid, so our nitrate is neutral. Is that kind of making sense for these salts so far? Maybe? So KBr is kind of the same. So right, potassium comes from potassium hydroxide, and then bromine, hydrobromic acid, so again, neutral. So let's kind of look at the next condition. And so what you'll see is, like, once you establish a salt is neutral, right, then you kind of know it moving forward, right? So we can know, oh, well, sodium's always neutral. So that also kind of helps. And so let's try the next scenario. So now it says, if our salt cation is the counter ion of a strong base, okay, and so that's basically saying our cation is neutral, because it's from the strong base. So let's go through our analysis. And the reason why I'm doing this analysis like this, I probably should have explained better, is that we have to analyze both our cation and our anion to see whether they're acidic, basic, or neutral. Because we could have, right, an acidic cation and a basic anion, or, you know, in this case, we're kind of focusing on when one is neutral and the other is not. So our first case was, right, they were both neutral. So they both came from either a strong base or a strong acid. But now let's look at the next step. So now it's saying, okay, well, we have a cation that's neutral, right? So we have sodium once again. So sodium, we can write it if we need to, but it comes from sodium hydroxide. So sodium is neutral. We've already established that. But then what about fluoride? What's its corresponding acid? And so go back right to the chart if you needed. Where's fluoride? What acid does it correspond with? So what acid does it come from there?
I don't know.
So it's right across, right? So
Oh, on that chart.
yeah, so on this chart, otherwise you just have to think of it, right? So just add a proton to our fluoride, because that's what makes it acid, so HF. Or, you know, this chart spells it out directly, okay? It's HF. But then what is that telling us? What did we remember about HF? Right. Yeah, so not a strong acid, so it's a weak acid, equilibrium. But then what is that telling us about the fluoride? So let's analyze this before we jump to the words. And so now this is saying that we can actually have some equilibrium, but we have to treat fluoride just with water, right? So let's just say we've added, again, sodium fluoride, we've testing it, we added it to our water. So we already determined our sodium's neutral, right? So sodium's just floating around in solution. But now what about our fluorine interaction with water? So we established this will do something, again, because it's weak, so it's going to reform HF. So that's what happens. So our fluorine, or fluoride, plucks off a hydrogen here. So then we make HF, but then this is a key point, is that we also make hydroxide. So then by our definition, our fluoride is a base because it produces hydroxide. And so this also kind of goes with what I said. So remember I said cations are usually acids, and anions, if they're anything, they're going to be basic. So that's what we're seeing here. And then let's just read through the words so that we can, what we just went through matches. So we said, okay, the salt cation was a counter ion of a strong base. Okay, so that makes it neutral. So, right, our sodium is neutral, calcium's neutral by that, potassium is neutral. But then it says our anion is the conjugate base of a weak acid. And so far we just did the analysis for sodium fluoride, but we found, right, sodium fluoride, and then it mentions, right, a basic solution will be formed. So now we kind of prove why it's a basic solution, right, because it's reforming our acid, yes, but then it leaves behind hydroxide, so that's our base. And so let's just see that with our calcium acetate as well, just so we can see the analysis and then also the reaction. And so now we have calcium acetate, and I still can't remember the formula for acetate. And again, right, we do our analysis, so we say calcium, from calcium hydroxide, we've established calcium as neutral. But then we look at our acetate, and so we can remember, so acetate comes from acetic acid. And again, we want to just emphasize what it's going to be doing and see how it creates a basic solution. So then our sodium acetate, right, reacts with our water. And then, of course, reforms our acetic acid. And I'm drawing it this way just because this makes more sense to me. So I can actually see the structure. And then again, right, our base is formed. So we pluck off a hydrogen from our water, leaving us with hydroxide, which is our base definition. And so we could repeat this same thing with the nitrous. So we could add a proton to this and make nitrous acid. And let's move on to the next scenario. And so this is kind of what I was saying, is that we only have so many acidic cations. So, right, these are usually amine or ammonium base. So I'm going to say usually ammonium salts, right, like that methyl ammonium or some sort of variation. And so that's what's shown here. And I think it's kind of telling that the example only showed ammonium chloride. But let's go through the analysis. So we have ammonium chloride, and So we already established that chloride comes from HCl, so this is going to be neutral. But now we're trying to figure out our ammonium, and again, cation, so I'm expecting it to be acidic if anything, or it's neutral. But you probably will just have to recognize our amines. And so then again, I want to show it reacting with water, because that's what matters. It's reaction with water now. So now reacting with water, what's it going to do? And so it can donate a proton. And so our water is going to pick up that proton, reform ammonia in solution, but then it leaves us with our hydronium, which gives us our acidic solution. So that's why we say this is an acidic salt then for ammonium. And I'll just write there like methylammonium as well, just so we can remember, right? So some sort of ammonium variation. And then the last little thing we mentioned was if we have, again, a highly charged metal ion, so usually aluminum, but could, be any other metals, iron, whatever, et cetera, et cetera. So manganese. So all of these highly charged metal ions, then our cation is generally acidic, and so sometimes you can have an acidic solution being formed, such as like aluminum. So aluminum is, again, what we'll see in our class. And so last little bits here is, we probably won't do this for our purposes, but this is just kind of more of what if. So what if we have ammonium fluoride? And so the question is, right, is it going to be acidic or basic? And well, that's not obvious because we have ammonium, which is an acid. We have fluoride that we said was a basic salt. But then it says that HF is a stronger acid than ammonia. So therefore, the Ka of our ammonia is larger than our Kb of fluoride. And so another useful thing is Ka times Kb is also equal to Kw. But again, for our class, we probably won't do this. So this would be a way to figure out like your Kb and Ka directly and compare them as well numerically. But it's probably okay for our class. All right, see if we can do this last problem in our few minutes of class. And just kind of where we're at. So it looks like we kind of finished the section. And on Wednesday, I think we'll go over kind of the solutions homework. So some of this colligative properties stuff. I noticed people were having some issues in like the lab and people asked about that. So we'll do that on Wednesday. And then probably also practice our stoichiometry with molarity and kind of practice. All right, see if you can try this in our last few minutes. Or actually, let's see if you can write this down because I think the other class is going to come barging in. So write this down and we'll pick it up on Wednesday. We'll just start off with this example because we only have 2 minutes. The other class will come in. So yeah, we'll end there. We'll pick up, see if you can kind of think over this tonight if you're confused. Wednesday we'll go over everything. It'll be a good day to ask questions, kind of catch up on stuff that we maybe rushed through. Then we'll do some demos. All right, thanks everybody. Okay,
Hey, Heston. You need these?
see ya. Have a good one. right. And then I shared the live notebooks. You can catch up.
Do you want our homework in place right here?
Oh, yeah, you can just throw it into that pile now.
Thank you. Oh, yeah, I just wanted to know, this is for, should the arrows be going both ways, because at
All
this
right.
point,
It goes whichever way, it should match the color. So if it goes darker, then it shifts to the right, and if it goes lighter, it shifts to the
even for
left.
just like the first one, that's just the combining the two.
For the first one though, that should just be like your standard, right? Because you have your, yeah, so that one doesn't have a shift.
Okay, so it's fine, just have them going both ways.
Yeah, that's fine, or no.